Hello everyone, I'm Kenji Tojo, a master's student at University of Tokyo. Today I'm going to introduce neural motion compression using frequency adaptive Fourier feature network. Character animation is essential in many video games. Under the hood, these animations are typically implemented using state machine that stitches together a bunch of animations given the user's controller input. In real life, the state machine is very complex and contains tons of animation sequences. Hence, compressing animation sequence is important to make the most of the limited storage resources to implement immersive animation systems. There are many works for compressing motion sequences. However, previous techniques requires handcrafted algorithms to exploit smoothness and redundancy in the natural motion. In contrast, neural networks can learn important features in the data. Recently, neural implicit representations have been applied to various types of data, including 2D images and 3D shapes, and shown to be able to reconstruct highly complex data using a compact neural network. That means they can work as learning-based high-quality compression algorithm for general data. In this research, we investigate a neural motion compression, a learning-based algorithm to compress character motion sequences. Given an animation sequence, our goal is to find a compact neural representation of the sequence without losing its visual quality. We do this by training an implicit neural representation of character motions that predicts the pose of the character from a scalar time t. Here, the character pose is represented as an m-dimensional vector that contains root and relative translations and rotations of each joint. Now we have input and output. However, it is not straightforward to train a standard neural network directly using these time pose pairs as training data. The input to our neural representation is time, a simple one-dimensional and linear signal. On the other hand, the output pose is high-dimensional and consists of complex and periodic signals. Remember the shaking head, elbow, and hand of the dancing character. Predicting such complex and high-dimensional motion data solely from the scalar time input, it's challenging when using a simple network architecture, such as multi-layered perceptrons. This is a common challenge in neural implicit representations. Previous implicit network relied on a technique called the Fourier feature to overcome this problem. In the case of the 2D image, input coordinates, that means x and y, are first mapped to the Fourier feature using trigonometric functions with various frequencies written in omega. The Fourier feature is then used by the MLP to predict the image pixels that contain rich and high frequency information like this lion in the RGB image. We draw inspiration from these studies and use the Fourier feature to reconstruct the motion sequence from the scalar time signal. Here, the choice of the Fourier feature frequencies can affect the dimensionality of the encoding, and thus the neural network size, and therefore the compression performance. Although previous studies typically randomly sampled Fourier feature frequencies from a probability distribution, such as a Gaussian distribution, this can add many non-effective frequencies, and which is undesirable for our compression purpose. Instead, we propose adaptively determining a small yet useful set of frequencies for motion compression by leveraging the periodic nature of human motion. And please remember that the character's hand oscillates periodically, and his head and foot moves like back and forth, and that is a periodic motion. So, specifically, we incrementally find and add a dominant frequency of the motion during training. Next, we describe our incremental training algorithm to adaptively find important frequencies to add to our Fourier feature. Once the training without Fourier feature is completed, we compute the training residual, that is a difference between ground truth and the predicted sequence. We then perform a DCT of the residual and find the dominant frequency, omega 1, of the residual. We next retrain a network with one additional Fourier feature frequency, and then again compute residual between ground truth and trained data, and then perform DCT of the residual and find next frequency to add. We repeat this process until a quality threshold is satisfied. That means the final residual RK is smaller than some threshold. Then our Fourier feature frequency is omega 1 to omega k, and the training is completed. Next, I will explain a network architecture. Here is the architecture of our MLP. We use a small MLP with 3 layers and ELU, or exponential rectified linear unit, as the activation. The ELU is known to be an effective activation function for predicting character motions. For more details about the architecture, loss, and training procedure, please take a look at our paper. Finally, let's take a look at compression results. Here is a plot where we fix the number k of Fourier feature frequencies and apply our method to 116 sequences randomly sampled from CMU mocap database. We fix k because we want to control the network size and compression ratio. That means we instead of testing the residual magnitude, we repeat adding Fourier feature frequencies until the frequencies are the specified number. With k equals 10, we can see that our method can compress motions with small reconstruction error. And CMU dataset contains some corrupted data, and our method fails on these data. For example, this input motion has high reconstruction error above 10% of the character's height. However, when we take a close look at the data, we can see that the input motion has noisy foot motion as seen in the trajectory visualization and in the down below. Next, we compare our method to two baseline approaches, which is SVD and naive choice of Fourier feature frequencies. The naive choice of Fourier feature frequencies uses consecutive integers 1, 2, 3, 4, and so on as frequencies. And we can see that for the tested 2 motion, our method plotted in gray achieves the best reconstruction error for a given compression ratio. This suggests that our frequency adaptive implicit representation works very well as compression algorithm, and that the adaptive selection of Fourier feature makes sense. Finally, let's take a look at the visual results. The red is the original sequence and the blue is the edge time compressed sequence using our method. We can see that the difference appears to be very small, and our method can reconstruct the motion with very high quality. Here, let's sum up the talk. We present a motion compression algorithm using an implicit neural motion representation. And technically, we present an adaptive selection of Fourier feature frequencies based on iterative training and a residual and a DCT of the residual of the training loss. And we tested our algorithm on a CMU motion capture database and showed that it can compress motion sequences with small error and outperformed baseline methods, including naive choice of frequencies and SVD. And here's the future work. One future work is comparison to the state-of-the-art methods. And in this study, we only compare our method with a very standard approaches. So comparing our methods with more sophisticated previous approaches will be interesting. Another future work is to encode a common motion styles for better compression results. For example, there is a common motion styles such as walking and running sequence. So learning a common motion prior from large database will be interesting and important to achieve better compression results. That is the end of the slide. Thank you very much for listening.